So we just talked about reflection. I want to talk about refraction as well, or maybe you've done this in a different order. It's okay either way. But what I wanted to, let me see if I can get this. There we go. Should have done that before I started, right? Okay, there we go. So what I wanted to talk to you guys about was now refraction, okay? So for refraction, what that means is light is now passing into the next material. It's not just bouncing off of it like a mirror, right? With a mirror, it never actually made it into the other surface. It just bounces off of the surface, and that's why we get that shimmer, right? Because the light's going immediately back, okay? And even with this, there's probably some slight penetration, but not much, okay? But you can imagine that for a glass of water, you know that light goes into it and it bends in some weird way, doesn't it? Because you can see it getting magnified. It magnifies things on the other side. And that's also a strange effect, okay? But what's happening is when light passes into a new medium, a new thing, right? A new object or material, right? We call that refraction because it's going to bend. If, and only if, these two things have different ends or indexes or indices, I guess two of them would be indices of refraction. And really this means basically density of the material. That's what it kind of comes down to. How light behaves in that material, and usually it's based on density, okay? So realize that for air and water, that's why I have these blue lines in here, this is supposed to be water, okay? Air is a lot less dense than water, isn't it? So when light goes into water, it actually slows down. I'm going to show you guys a video if I can remember to, okay? Light slows down when it goes in, and because there are different parts to light, different rays that come into the same surface, they slow down, and because they're at slightly different angles, they actually slow down in different ways, and they bend as they go into it. I'll see if I can find that video and show you guys that as well, okay? But as light comes in, it slows down in the denser medium. Any time light goes into a denser thing, it pretty much always slows down, okay? So if it's in a vacuum, it would have basically no index of refraction. It would have no density because there's nothing there. So light bends even when it comes into the atmosphere, which you can see because you see it during the sunset, all right, or the sunrise. You actually see that red sky. It's partially because of refraction, okay? Other things happen that are weird with that as well. Like if you ever notice, sometimes as the moon is rising up, like on certain times, right, if you can see a full moon right at the horizon, it looks huge. It looks huge because you have refraction happening, which actually magnifies the moon. And as it gets higher into the sky, it actually looks smaller and smaller as it gets up into the sky because there's less of a refractive thing happening. You have less material, right? You have the whole of the horizon between you and that moon. And then as it goes up above, you have less material, so you get less magnification. It's a strange thing. Also, the angles kind of mess with you too, okay? But as light comes through, it bends. The denser the material, the more the light bends. And it does this in a regular way. We know this already. You guys have seen plenty of things like this, like light going into a glass of water. But let me give you a good idea, okay? Here's another one down here. Hopefully you guys can see this pretty well still. I had moved it before. But as light goes into this block here, you're going to see that, again, it has a slight bend to it, doesn't it? If I go straight on into it, now that's interesting too, right? If light goes straight into it, again, the perpendicular matters here, okay, so that's why I've drawn it out. The incident angle matters here, that theta matters, okay, but if you're straight down, light's just going to go straight through because it has no chance to bend going through it. It only has a straight line path to go through, okay? But if instead you're going through a material like this, all of a sudden you can see, do I have a closer path for this thing? I think I do from here. Let me do that. Plug it in over here, right? Unfortunately, I have to have it plugged in because lasers tend to use a lot of energy. But let's see if this works. Hopefully. Nope. Okay. Getting there, guys. What you're going to see is that as light goes through this block is much denser than the air around it. So you're going to see light get bent as it goes through this block. So let me see if this actually still works now. Hey, there we go, magic. All right, so now this thing has a nice foggy back to it. You can kind of see there, so you can actually see it. Let's not knock over my coffee. That would be bad. Put it higher so it has more effect when it hits things, right? But as you notice, right, so as the light beams come in here, you can kind of see, let me put my hand in front of it perhaps. You can see now, aha, look, so you can see the light ray against my skin, and then look what happens when it gets into the block. If it's straight on, it basically continues, but if it's at an angle, you can see that it gets bent, right? And the more of the angle, the more of the bend in there. You see how that's not going at the same angle, right? As soon as it gets into that material, it bends. And you can actually see as you change the angle of incidence, so just by changing the angle, you can change by how much this thing bends as it enters this material, okay? So, there you go. As it goes in, your angle of incidence affects your angle of outcidence, your refraction angle, right? Your angle of refraction, how it passes through, the angle it makes against the perpendicular inside of the material, right, is different from what it makes going into that material, okay? So that's all well and good, okay? But there's also another thing that affects it, and that is, of course, not just the angle at which it hits it, but also the density of the material. If this was glass instead of plastic, you'd see a slightly different angle still, okay? And in fact, I might have a couple things here. We're going to look at them later. I don't have any straight blocks. That's unfortunate. I wish I did. But as light passes through glass, it'll bend a different angle than it does through water, than it does through, plastic. Plastic might be, depending on the kind of plastic, it's usually lighter than water, so it might bend less going through plastic than it does through water. Glass is sometimes often, right, if you drop a piece of glass into water, it's going to sink, right? So glass is denser than water, so it'll bend more as it goes through there because the index for refraction has pretty much everything to do with the density of the material. And if that changes, then the angle at which this thing comes out also changes without even changing the angle of incidence. So two things can change your angle of refraction. The angle at which the light comes in and the difference in the density between these media, or these mediums, right? These different material. And the relationship is pretty easy. So we account for both of those things, the angle at which this thing's coming in and the difference in density between the materials through something called Snell's law, all right? So Snell's law is very, very simple. There's nothing too crazy to it. It just says the index for refraction, or basically something related to the density of the first material, times the angle, sine of the angle of the incidence, right? Angle at which it's coming in, we're related to its perpendicular, is equal to the index for refraction, basically the density of the second material, right? Times the angle of refraction here, okay? So the refractive index of the second media and the angle of the second media, okay? So the angle at which it comes out is related to the angle at which it comes in and also the difference in the density of these materials. So let's do some really cool things, okay? So have you ever heard of a mirage before? I'm assuming you probably have, right? People see water in the desert. Why? Because what happens is air. Think about hot air balloons. Hot air balloons rise, even though it's still filled with air. It is still filled with the same exact material as the outside of the balloon, right? But it's hotter on the inside, so that bubble of air expands because it gets hotter, okay? Well, the desert floor works the exact same way. That sand gets hot. It gets hotter than the air by a huge amount, okay? So in Death Valley, I think the highest temperature ever recorded was about 131 degrees, which is just very recently. But if you actually check the temperature on the ground, it is often hot enough to actually fry an egg. You can actually cook an egg on the ground, especially on asphalt, because that holds on to the light. The black color absorbs light. That's why it's black. It's not reflecting back at you. Like my hair, very different from my skin, right? My skin is highly reflective, reflects most of that white light back at you, whereas my hair is brown, and so it absorbs most of it. My hair actually gets pretty hot on a summer day, okay? That's why I like it short, right? But, so that's basically it, guys. You can figure out the angle at which this thing is going to come out based on these two things. And again, with parallel rays, you should have the exact same thing happening for a nice flat surface. You got a flat surface with a level, calm, unmoving, unwavering, level of water inside of it. The light rays that come in are going to get bent. If they're parallel, they're going to get bent, according to the perpendicular of that one, to the exact same extent. And they're going to be parallel coming in just as they were coming out, as you saw on that block, okay? So nothing too crazy there. That's pretty expected, all right? So again, as long as this thing is parallel, there's our perpendicular there, so it's going to come out at the same, if we can draw this properly, it's going to come out at the same thing, and all these light rays are going to be the same spacing here as they were coming in, but just at a new angle, all right? Where this also gets interesting is just like with reflection, okay? Just like with reflection, what happens when we take and we curve our surface? So I'm going to erase this. Actually, I'm going to erase this over here so you can see this still, okay? So I'm going to get rid of all this because you can rewind it and go back to it anytime you like, all right? But let's now draw a new surface. Let's say we have a nice meniscus of water. And that's actually what happens, right? If you guys have taken chemistry, you don't ever actually have a flat surface. You get a nice meniscus or a bubble of water like this. And sometimes with other things like mercury, you get some kind of a crazy meniscus that's kind of inverted there. But you always get like this bubble because you have surface tension of water holding it together, okay? So what if we get actually a bubble of water like this? Or we take a Ziploc bag and we kind of make it have that kind of an edge to it, right? Well, when light rays come in, if you've got this very top spot, right, the tangent is pretty much exactly flat there. So, our perpendicular to that is going to look very much like this one. Here's our incident ray. Oh, gosh, that's a totally straight incident ray, isn't it? Jeez. Okay, let me redo this. So let's get a nice straight incident ray, hopefully. Okay, so now this is air, and this is water in here. Okay, so this is denser than that, so it's going to bend, and when it bends, it's going to bend towards that. Okay, it's going to bend towards this perpendicular line if it's a denser material inside. Okay, so there's our theta 2, there's our theta 1. But as we know, as we change our angle of incidence, we change how this light ray comes back out at the end. So what happens if all of a sudden I get a light ray that's parallel initially? It's going right alongside this guy, okay, but it hits the surface here. And now our flat is more like this. That's not quite right. It's more like this, right? But it's curved compared to that surface up here, right? It's at a slightly different angle. So here is our flat. Our perpendicular is now going to be like this, just a slightly different angle, right? But that's now enough to make this light bend maybe down like this instead. And so it comes out like this and has a slightly different path from the other ray. And if you look here, that light is going to be in the exact same spot. If you look here, it's going to have switched places, right? And so on this side, not only does it switch places, but it's also actually kind of closer together, all right? And what about another ray? Another ray that's also parallel, okay, but it hits the surface, let's say over here. It hits over here. Well, now it's tilted this way, so our perpendicular is like this. So it's going to bend it, but it's going to bend it down like this with respect to that perpendicular. And that's going to come out like this. So maybe that light ray focuses down here, okay? But you can see some really strange things happening. If they're nice and tight together at the beginning, you can see that they're going to have a focal point where all the light meets up again, okay? And that's a really interesting thing. When you get to this focal point, sometimes light that was nice and tidy and right next to each other starts to become flipped, all right? Sometimes what you get is, as this comes through, this thing might actually come through over there. And so the light that was on this side before may actually get to be on the other side of this focal point. At the focal point, it all matches up nice and tidy, but on the other side, it flips around. And that we talked about with reflection as well. But one thing I want to now tell you guys is if you had a picture, right? If this was something that's got a direction to it, I don't know, like, why can I not think of anything? If this is my coffee cup, there we go. I don't know why, but if I have my coffee cup and I'm shining the light off of my coffee cup, right? Here it is. It's nice and tidy coffee cup here. Totally clear exactly what I'm talking about there, right? Here's my coffee cup. The light rays coming off of that thing come through here. They get bent before, right? So maybe if you have a nice flat block, you'd actually see a coffee cup, but you'd see it offset, okay? But now, if you've got this curved surface, what can actually happen is something really crazy because these light rays are no longer parallel to each other. They're crossing each other because they're all getting refracted according to the perpendicular at which they're at, right? Their angle of incidence, which is very different, right, from here. So now you might actually get rid of that one because that was just going to confuse us. But when you see the image of the coffee cup over here, instead of it being this big, it's going to be a lot smaller. And the side that was the bottom over here, this is going to look like the bottom now. And this is going to look like the top over here. And so you're going to have a coffee cup that's exactly flipped. You're going to get an inverse image, okay? And what you call that is you get a true image. That is a true image. A virtual image is anything you see before that. So if you look over here, it's going to look bigger or smaller depending on where you see it over here, right? But if I draw my coffee cup here, again, purple is going to be towards the bottom of the coffee cup, and the red is going to be towards the top of the coffee cup. So I'm still going to have my coffee cup in the right direction here, but it's going to be right side up. That's a virtual image. So anytime you get basically before the focal point, between the image and the focal point, you're going to have a virtual image. Anytime you get past that focal point, you're going to have a true image. And a true image is always flipped on its head. So fun thing for you, try and find a magnifying glass around your house. When you do, take the light from a fan or from a window and try and shine that magnifying glass on a surface, maybe a piece of paper, something nice and clean and white that you can actually get a good background on, and then try and focus it. And eventually you're going to find a focal point at which you can make an image. Okay, a focal point is just going to have a really bright spot of light. Okay, all the light's coming to one spot. But if you get past the focal point, what you're going to see is you're going to see that image of the window or the light or the fan, but it's going to be flipped on its head now. If you get closer than the focal point, what you're going to see is that light or that fan, right, or whatever, but it's going to be smaller, much smaller than the window or the fan, and it's going to be right side up. So, virtual image between the object and the focal point, right side up, and you can make it smaller or bigger depending on how things work out with the curvature of the surface. And the true image, right, again, you can make it larger. The farther you go out here, the more those lights are going to disperse now, right? Those light rays are going to keep going straight out in that direction, but they're going to get wider and wider apart, so you can actually take and make the image larger farther away. And this is how magnification works. Magnification works by having light rays that cross, right, and either taking and shrinking it down if you want to, reduce the size of the thing, or if you want to increase the size of it, you have it expand outwards, let those light rays cross, and then come back on the other side. And when you do, you can make something that was maybe this large, like a bug. If you have those light rays cross enough, they can disperse out. You can make your bug look huge so you can actually see it in detail. Same thing works for reflection. So Newton was extremely smart. Everybody else had been making lenses like this. Newton decided to do the same thing with a mirror, with reflection instead of refraction, and made a much lighter weight magnifier. Right? Newtonian optics. If you want to look that up, his telescope is kind of a really good idea. I still use it a lot today. All right, so last thing I want to show you guys. When you have a curved surface, it no longer just goes straight through, but it starts to do some crazy things. So let's take a look at that. And let me see if I get my hand in the right place here. I got too many things going on, right? And then I got the light there. Okay, so don't shine in your eyes. Don't shine in your eyes. Don't shine in your eyes. Okay. So now you can see straight on in, no angle of reflection, and you're going to see that if I change my angle of incidence, I start getting a change in my light going into that material, right? It starts to bend as it goes in. Very slight bend, but it does get there. And then we're going to talk about that last thing you see up in the top, right? We're going to talk about that in a second. But on the way out, things also get interesting too, because you'll notice that it refracts again because it's leaving the denser medium and it's going to a much lighter medium. It's going from plastic to air, so it bends again on the way out, okay? And so from that, you can actually take, and you can really mess with how, now you can see, this thing's getting closer together because the light rays are hitting a curved surface and they're coming through. And then once they leave, they basically usually go in a fairly parallel path, but they bend in another predictable way. And again, you can kind of see, here they're kind of parallel once they get out. But inside, right, inside, they're actually totally bending to get to a larger and larger, closer and closer to a point. Right? And you'll also see interior to that, so kind of interesting against the background of it, you can maybe see some really faint lines coming back, hitting this far surface, and then bouncing back out. Anytime light encounters a surface, okay, anytime it encounters a, gosh, why am I blanking out on this right now? Anytime it encounters an interface between two materials, light will reflect slightly, okay? So you'll have refraction, but you'll also have reflection back out of here. You almost never just have one. If you're going to have one, you're probably more likely to have reflection than refraction. But with refraction, you also get refraction. Reflection, you get reflection. With refraction, you get reflection and refraction, right? So you usually have light rays coming back out also, again, equal to the angle of incidence. Last thing I was going to say, go on brain, you can track with me here. As you're going through all of this, there is a special angle. So if you bring this straight up, things are going to go straight through, okay? But if you bring it to a magic line far enough out, what you're going to find out is that if you go far enough out, here's your your interface, right? Air, water, right? If you go far enough out, what you're going to get is a critical angle. And at that critical angle, things are just going to basically try and travel. Things are going to basically just reflect back out. Okay? So when you saw this thing right here, you actually saw lines going in, they got bent. Light gets bent as it comes through, according to the perpendicular. But it was hitting some kind of a critical angle here, and then it was completely 100% reflecting. It was reflecting off of that surface and then back out this way. So, again, perpendicular to that surface, that angle and that angle were equal. You'll see this critical angle at which it 100% reflects the light back out, and no light actually comes through on that one. If it hits that critical angle, if it's far enough out, it'll just reflect back out. Okay? No more refraction through there. Kind of a cool thing.